Well, hello and welcome to Math 315, Analysis and Topology, and I'm going to do the first recording for this section. Each section will be divided roughly into 4 parts. Each video will go for roughly about half an hour, some a bit shorter than that because it will take you some time to copy in the bits and pieces, and also you might want to pause and reread and think about things along the way. You should print out the notes from Leo, because as you'll see there are various places where there are gaps in the notes, and I will get you to copy in the particular solutions to various questions as we work through them. So I want to begin with saying a little bit about what exactly is analysis that we're about to undertake. And to understand this, we really have to go back to the time of Isaac Newton, when he developed or co-developed with Leibniz the calculus. Newton invented an object that came to be called an infinitesimal, which was essentially a quantity which at one point is not zero, and so you could divide by it, and then suddenly it became zero when it was convenient to do so. This was criticised by a number of people and referred to unkindly by his critics at the time as the ghost of a vanished quantity. Now, the problem was that Newton used these and other objects called fluxions to obtain amazing results in physics that were not only true but quite groundbreaking. And in fact, Newton was very loath to publish his work on calculus, which is why Leibniz probably published it first, even though Newton may have discovered it beforehand. And he used the calculus to get results, but then he went back and tried to prove the results using geometry and geometric methods. It took him a while before he actually published anything on calculus. His mathematics was essentially correct, but the problem was, without the limit concept that we're going to be studying in some detail, he was unable to clearly explain exactly what he was doing. And his ideas soon caught on, and the differential and integral calculus was born. Now, unfortunately, in the hands of less able mathematicians, problems began to arise because you could misuse some of these ideas. If you take away the concept of limit, you could misuse some of these ideas and ideas regarding the infinite in general. This led to results that were patently ridiculous. And I'm going to actually begin with a piece of nonsense. I'm going to show you, I'm going to prove, incorrectly of course, the following result. I'm going to prove that if you add up the numbers 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 forever, then the answer is 4. Now this is clearly crazy, but I'd like you to think about where the mistake lies in my so-called proof. Where's the mistake? So I'm going to begin by, here's my so-called proof. So I'm going to begin, I'm going to take the number 1, and I'm going to write it as 4 minus brackets 4 minus 1. Now if you take the brackets out, this is a perfectly correct statement. The 4 minus 4 is 0, minus times a minus is plus, so this just says 1 equals 4 minus brackets 4 minus 1. That's a true statement. I'm going to take the number 2 now, and I'm going to write it as 4 minus 1 minus brackets 4 minus 1 minus 2. So that gives you 4 minus 4, that cancels, minus 1 plus 1 cancels, minus minus 2 is 2. So ditto, that's a correct statement. And I'm going to continue the pattern now. I'm going to write 3 as 4 minus 1 minus 2 minus 4 minus 1 minus 2 minus 3. And again, I invite you to take the brackets out, and it will collapse back to 3. And 4 I'm going to write as 4 minus 1 minus 2 minus 3 minus 4 minus 1 minus 2 minus 3 minus 4. And again, this is a perfectly correct statement. And then I'm going to say, and so on forever. Now, what I'm going to do now is I'm going to add up the this infinite left-hand side that goes on forever. So it's 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 and so on forever. But look what happens on this side. The 4 minus 1, the minus 4 minus 1, that term cancels out with this one. This term cancels out with this one. This term cancels with this one. This cancels with the next one, and so on, because it goes on forever. All of them cancel, and the only thing that survives is the number 4. Now, by the way, there's nothing sacred about this 4 here. I could have put 44, or I could have put any number I like in here, and I can still make this sum add up to it by this silly argument. So I've added up the left-hand side, and we get this desired crazy result, since all the terms cancel, leaving just the number 4. Well, what on earth has gone wrong? Where was the mistake? And the problem lies in this word and these words, and so on forever. The problem lies in not being clear about and what so on forever means. And that's where these sorts of problems arise, when we start playing around without taking due care with the infinite. And we'll come back and look at this whole issue later when we look at the whole question of infinite series. How can we make sense of infinite series? How can we make sense of this and so on forever idea? Slightly less dramatic example, but one which I think is quite important, is that if we draw the graph of y equals x squared minus 2, so you should have a mental picture of that one. So I'll just draw it quickly here. So y equals x squared minus 2. So here it is, it looks like this. So it's got to cut the y-axis at minus 2, and it looks like that. X and y are real, so there's my y, and there's x. Well, it's fairly obvious that this graph cuts the x-axis, surely. On the other hand, if I now insist that the x and y are rational numbers, then it doesn't cut the x-axis, because these points here, this is root 2, and this is minus root 2, and these are not rational numbers. So in this case, the graph of, if I insist that x is a rational number, then this graph doesn't cut the x-axis at all. What exactly do we mean by this idea of continuous? We say that this is a continuous function. You can draw it without taking the pen off, but what does it exactly mean? If you change from the reals to the rationals, this doesn't cut the axis at all. It's not even continuous. So we're going to worry about what this word continuous means very precisely. Another idea we're going to visit fairly soon is this idea that we say that the function 1 over x, as x goes to infinity, whatever that means, then 1 over x goes to 0. That is, if x becomes extremely large, then 1 over x becomes extremely small. But how can we capture this idea very precisely? Exactly what does it mean to go to infinity and to go to 0? These are some of the questions that analysis attempts to sort out. Here's another one of my favourites actually. Heuristically, I should say. Heuristically means just by common sense. When you say heuristically, it means just by experiment, by common sense. We might think that this sequence here, this 1 plus 1 over n to the n, gets closer to 1 as n becomes very large. Because after all, if n is very large, then 1 over n, you might argue, is very small, so this is roughly just 1, and then 1 to any power is 1. However, if you try it on your calculator, you'll get a nasty surprise if you haven't seen this one before. If you put a big value in for n, try it on yourself. You might like to pause the video and try it yourself. Put n as, say, 10 in, put n as 100 in, put n as 1,000 in. You're not going to get 1, even though heuristically, common sense says, well, you probably should get 1 because this is small and 1 to anything is 1. You can try it on your calculator. I can recall many years ago, in a first year tutorial, I put this on the board and I asked the students what happens as n gets very big, and one very confident student yelled out 1. I said, that's interesting. Get out your calculator. So he got out his calculator and he put n as 10 and 100 and 1,000, And of course he wasn't getting 1. In fact, he became quite angry. I thought he was going to smash the calculator. And so that led us then to discover what this limit in fact is as n becomes very big. And we will look at this particular limit later in this course if you haven't seen this one before. So analysis then, what's analysis about? Analysis then is an attempt to make sense of a lot of mathematics that's connected with functions, with limits, with derivatives and real numbers, and also integration. But in this course we're not going to have time to look at the analysis of integration. We will be looking in great detail at functions, limits, derivatives and real numbers, and in fact sequences and series. I suppose I should have added in there as well. So that is, we're going to try to be very precise about what these things actually mean. This work started with people, we'll come across at least this guy's name, Cauchy and Weierstrass. Cauchy was a French mathematician, Weierstrass was a German mathematician. Cauchy's in the 1700s, Weierstrass a little bit later. And these people were very, very concerned that wrong results were appearing as a result of sloppy mathematics, of people not being very precise about what these ideas meant. What does "and so on forever" mean? What does continuity mean? What do limits mean? What are derivatives? What are real numbers? And so on. Now today, analysis is a very central branch of modern mathematics. But I do stress to you it's also a very hard one. This is not going to be a particularly easy course, but I will attempt to make it as clear as possible to you. Explain the mathematics clearly, that is. And also I'll give you a lot of guidance on what you need to be able to do, what things you really need to know in detail. So although it is a hard subject, we will hopefully get through it and enjoy it together. Okay, so we're going to begin with some basic tools, and in particular we're going to need to be able to deal with what are called inequalities and absolute values. We're going to do lots and lots of inequalities, and also we'll be dealing with absolute values as well. So I thought we might just revise some of our basic facts about inequalities and absolute values and do some examples on working with these. So here are some basic facts. They look complicated, but if you put them into simple English, they're not that difficult to see. This just says if you've got x is less than y, and it's always nice to think of a little picture with this. So I like to draw little pictures all the time in maths. So when you're looking at this, think of a picture. So there's x and there's y. So x is less than y on the line. You take z to be a positive number. Z bigger than 0 is another way of saying z's positive. And if you multiply these numbers by z, these numbers by z, you get xz and yz, and it preserves the order. So if you multiply an inequality by a positive number, nothing happens to the inequality sign. And similarly, you can divide the inequality by a positive number. You can do x over z and y over z, and that inequality sign stays the same. On the other hand, as you may recall from school, if you multiply both sides by a negative number, so if z is less than 0, that is z is negative, then it flips the inequality sign around when you multiply, and it flips the inequality sign around when you divide. So the less than becomes bigger than. The third one is if you've got x and y, x less than y, and both bigger than 0 for this one, then if you take 1 over x, then that's bigger than 1 over y. So 1 over x will be bigger than 1 over y. So if you've got two positive numbers, one less than the other, if you turn them upside down, then it also flips the inequality sign around. These are basic facts you probably know from school. Similarly, you can add any z to both sides of an inequality. It still stays the same. And finally, if x is less than y and y is less than z, then you can say, well, look, x is less than z. So again, in the picture, I'm just thinking of this: x is less than y is less than z, and so x is less than z. In terms of the absolute values, the absolute value of x squared is just x squared, and x is always less or equal to the absolute value of x. Now I should just remind you, perhaps over the side here, about what the absolute value means again. So the absolute value of x, well, if x is positive, we'll make it positive or equal to 0, then this is just equal to x, it doesn't change. If x is negative, like for example -3, then to get the absolute value of -3, you've got to put a minus in front of the -3, so you've got to write -x. So that you will have seen before, but just to remind you, that's the definition of the absolute value of x. It's equal to x if x is bigger or equal to 0. It's minus x if x is negative. Also note that if a is positive, then we have absolute value of x is less than a is the same as saying x lies between minus a and a. And again, you might like to draw a little picture here. So here's my x, and if the absolute value of x is less than a, that means the distance between x and a, the distance between x and the origin is less than a. So that means this is the same as saying x lies between minus a and plus a. Well, just to come back to a couple of basic examples, you will have solved questions like this back at school, but worthwhile just reminding ourselves how this works. And so I'm going to now work through the solution to this one. So here it is here. So here's the question. We're solving the absolute value of 2x minus 3 is less than 7. Now, using what we just wrote down, that says 2x minus 3 has to lie between minus 7 and plus 7. So that's just expanding out what this means. Some people do it by cases. This is very complicated and very confusing. I think it's much better, and if you're teaching this at school, much better to write down that this lies between minus 7 and 7, and we get a nice simple equation. We don't have to worry about cases and so on, which are very confusing. So I simply add 3 to both sides, because I want to get rid of the minus 3, and so that'll be minus 4 is less than 2x is less than 10. And I can then divide both sides by 2, because 2 is positive, so it won't affect the inequality sign. So x is bigger than minus 2, less than 5. And we generally draw a little graph of this, so always mark in the origin. So that says x lies somewhere between minus 2 and 5. We put open circles to show that we're excluding the two endpoints, and we sort of draw a little region in between. Well, a couple of inequalities to solve, because we will be dealing with lots of inequalities during the course. And so we're going to solve this quadratic inequality firstly. So we're going to solve x squared minus 3x minus 10 is less than 0. Again, you would have done these back at school, and we just solve it here. So there's the question. We're going to solve x squared minus 3x minus 10 is less than 0. Now, there are various ways people do this. I'm just showing you my preferred way, and that is what I do. Firstly, I'm going to factorize the quadratic. If you see a quadratic, you should always factorize it if possible, and this easily factors to x minus 5x plus 2 is less than 0. What I now do is, but some people do cases here again, it's very complicated. I just like to think graphically, so I'm going to draw the graph of y equals this one. So I draw the graph of y equals this parabola, and it looks like this. It's just a parabola that cuts through 5 and minus 2. They're the roots of the parabola. Draw the parabola, and now if I want to see where is this negative, always put this into English, where is this quadratic negative, that means where are the y values negative, and the y values are going to be negative in here. So I can read off from the graph that the solution to my original quadratic inequality here, we simply need my x to lie between minus 2 and plus 5. Minus 2 and plus 5. There are other ways of doing this. I think this is the most instructive way, because when we get to cubic, for example, you do a similar thing. You draw the corresponding cubic and think of things graphically. So we're drawing the graph of this quadratic. The second example here is a little bit more complicated. It's 3 over x is bigger than x minus 2. And this one's more complicated. What makes it complicated? What makes it complicated is the x in the denominator here. So here is the solution to this problem. Again, you might like to pause and copy in the solution. Now, one is tempted to multiply both sides by x at this point, to multiply the x up here. And, well, as your parents taught you, you should resist temptation, because that's a very dangerous thing to do here. Some people, again, do it by cases. They look at case if x is positive, case if x is negative. My preferred method, and I don't mind if you do that, that's fine, as long as you do it correctly and you get the right answer and you do it carefully. My preferred method with all of these, I like one method that's going to solve all of these problems that have got things in x's in the denominator. I'm going to multiply both sides of the inequality by something that will not change the inequality sign. On the other hand, it's got to get rid of the x. So I multiply by x squared. And whenever I've got some term with x's in the denominator, I simply multiply both sides by the square of that quantity. Because x squared is always positive. Well, at least it's not if x is not 0. So I suppose I should write here x is not 0. If it's 0, doesn't make any sense anyway. So I'm going to multiply both sides by x squared. So I multiply this by x squared, I get 3x. This by x squared, I get x cubed. This by x squared, I get minus 2x squared. And just rearranging this now very carefully, I'm taking this term on the other side and then I'm reading it backwards. So you might just check that step there. It becomes x cubed minus 2x squared minus 3x is less than 0. So 0 is bigger than that, so this is less than 0. So just watch that step carefully there. Now out of this I can factor an x out. So I get x squared minus 2x minus 3 is less than 0. And then I've got a quadratic here, so I can factor the quadratic, and it factors like this. Now this is a cubic, and so again I'm going to draw the graph of y equals this cubic. So I draw the graph of this, and it's going to go through 0, it's going to go through minus 1, and it's going to go through 3. Now, this inequality is saying where are the y values negative? Where does it go negative? Where are the y values less than 0? And that's clearly going to be over here or in here. So this is 0 in there. And again, I can just read off the solutions then. So if I'm over this part, then the x is less than minus 1. And if I'm in this section, then the x is between 0 and 3, excluding both points. And there's the solution of the inequality. There are some more of these to practice in the tutorial problems. Now there are two very important inequalities that we're going to be using. And the first one is the triangle inequality, and this is our first theorem. So the triangle inequality says if you've got any real numbers x and y, then the absolute value of x plus y is less or equal to absolute value of x plus absolute value of y. Very fundamental inequality that we'll be using quite a lot. If you want to think of it graphically, if you think of the x's and the y's as vectors, then you can sort of draw a vector picture, so x and y, and then this will be the resultant x plus y. And all this says is that the length of this vector, the length of this side of the triangle, is less or equal to that length plus this length, which makes sense. That one has to be smaller than that plus that, otherwise you can't draw the triangle. Well, the proof of this is, I'm going to give a little proof of the triangle inequality, and here it is here. Don't need to memorize the proof, but you might like to try and follow it through. I'm going to use the rules 4 and 5 that I listed before. So I'm going to start with the left-hand side of this, and I'm going to look at the square of it. I'm going to look at the square of this quantity. So the absolute value of something squared is just the square of the number itself, so that's x plus y all squared, and I can square that out. It's x squared plus y squared plus 2xy. Now I'm going to use the fact that this is the same as that is the same as this one, and the absolute value of a number is bigger or equal to the number itself, and so 2xy is less or equal to 2 absolute value of x absolute value of y. And then I can factorize, this is just a quadratic, I can factorize this down, it's a perfect square. I can factor that to be absolute value of x plus absolute value of y all squared. And now I simply take the positive square roots of both sides of this, and we have the triangle inequality. You don't need to be able to reproduce that proof, but you might like to see how it works, to see how we're using these rules 4 and 5 that we listed above to give this result. Now you can repeat the application. This generalizes to this. If you've got an absolute value of a sum is less or equal to the sum of the absolute values. The second very important result is, which we're going to use quite a bit, is the arithmogeometric inequality, sometimes called the AMGM inequality. And what it says in English, it says if you give two positive numbers, then this is their average, and this is what's called the geometric mean. So this is the arithmetic mean, this is the geometric mean. So a plus b on 2 is bigger or equal to root ab. Now, so I'm going to give a little proof of this result, and the proof, again, you don't need to memorize, but you might like to follow it through. This material on AMs and GMs is in the extension 2 HSC syllabus, and so it's a bit of mathematics you should have quite a bit of mastery over. Okay, so it goes like this. Here's the proof of the AMGM inequality. So we start off with two positive numbers, and we're going to prove that the average of the two numbers is bigger or equal to the square root of the product. So I'm going to begin with a true statement, something which is clearly correct, clearly true, and that is, if I take the difference of two numbers and square it, whatever these numbers are, once you square it, it's going to be bigger or equal to 0 for all x and y. Now I'm going to square this out, so I get x squared minus 2xy plus y squared is bigger or equal to 0. And I'm just going to rearrange this. I'm going to keep these terms on the left side. I'm going to pull this on the other side and then divide by 2. So I get x squared plus y squared over 2 is bigger or equal to xy. Now because a and b are positive, then I can take x to be the positive square root of a, that is, I can write x squared as a, and I can write y squared is b, so I'm just taking y to be the square root of b, and if I plug those back in, I just get the desired AMGM inequality. In the first assignment, I asked you to give another proof of this using geometry, the way the ancient Greeks did it. and that's in the first assignment. Now, if A and B are equal, then we have equality. If you put A equal to B, then you get A plus A over 2, which is just A, and you get the square root of A squared, which is A. Now, so this theorem simply says that the geometric mean, or the average, of two positive real numbers is greater than their geometric mean. And as I mentioned, there's one of these in the assignment. This generalises, but I'll have a look at that in the next recording to see how the AMGM inequality generalises. The main thing you have to remember is this one. You should be able to state, you haven't got to give a proof, but you should be able to state this result. It's very fundamental. And we'll continue this in the next recording.